Okay, we just started recording. So we summed up the statics conditions, and now we're considering a sample problem. We've written equations for the forces and torques to cancel each other out, and now we're just rewriting them clearly. Okay, so for the b-axis, we have sine beta in here. Beta is 90 minus theta, so sine beta is the same as cosine theta. So clearly you can only have sine theta, cosine theta, right? So there are only two options. And that can actually be easily checked by a trick. So that's easy to fix. Now plus f sine theta equals n 1 cosine theta. And the center of mass axis gives us n2 plus f, or we can actually write it as, yeah, let's put it f for now, n2 plus f, or 1/2 sine theta. Oh, 1/2 can also be canceled. Sine theta equal n1 cosine theta. Okay, so this is probably as simple as it gets. For torques, let's look at these three equations and well, take a look. Take a minute. Tell me what you think about these three equations.
Should the last one have a subscript or with the n?
Oh,
or...
yes, n1. So do you notice anything about these three equations?
Well, you could set b equal to O and then cancel out an f sine theta.
No, I'm not asking you to solve them. I'm asking just to see a... So remember, we can choose any x's. I can pick a random point on the rod and write an equation for it, right? So the question is, does it make sense? Is it worth it? So the answer is obviously no. You cannot really have like 1,000 independent equations. You just don't have enough variables. So once you've gotten, like, say, these three equations, your first question is, are they independent? And are you guys familiar with the concept of independent equations?
Like one can't be derived from the other?
Pretty much, yes. One cannot be expressed as a combination of the others. Okay? So basically that means each equation contains independent amount of information. Is this the case for these three equations? What do you think?
Seems like you could get O from A and B. Oh, wait, no, because there's an n2 sine theta. Oh, wait, no, yeah, you can get O from A and B, I think. Yeah, you can get A by subtracting O from B.
Yeah, you could do that. Or you can say, oh, from A, you got that the mg over 2 cos theta term, the same as n2 sine theta, and replace it in the B equation. And that would make that equation equivalent to O, right? So they're not independent, which is good. Okay, that let's write it down. Not independent. And it helps to put a common y. You can say that O can be obtained from A and B. In fact, if they're not independent, then any of the three can be obtained as a combination of the other two. It just sometimes it's easy to see how one is obtained in terms of the others. In terms of A and B. Okay, that means you just decide which two you want to keep. It's totally arbitrary. I like equation A because it has fewer terms, so I'd probably keep equation A, and perhaps also keep equation O. But it's totally arbitrary. Okay. So now we need to understand how many equations do we actually need. And math-wise, we need as many equations as there are unknowns. So let's understand how many unknowns we got here. Let's count. I'm going to take my red pen and put question marks next to quantity that we don't know, starting with the force equation. So N2, we don't know, right? F, we don't know. M, we do know. G, we do know. And 1, no. So that's 3 unknowns so far.
Yeah.
Right? Now, what do we have here? Theta. Theta shows up.
It is known.
It is known. Okay.
N2 unknown, F
Yeah, that's
unknown, and 1 unknown.
Yeah, these all have been counted for. So we have 4 equations and what, only 3 unknowns?
Yes. So we should be able to solve.
Yeah, that means it's actually redundant. We may not be able to solve it. So it's not good to have more equations than unknowns either. So when the numbers precisely match. But yeah, well, let's go with it. And let's just recall one more equation that we want to write, of course. That is, because at the end of the day, we want to find the mu, right? So what is mu about? It's about the relationship between this f and the normal form. So f equals mu and 1. So basically, we trade the unknown f for the unknown mu. That doesn't affect the total number of unknowns. Does that make sense? So with this in mind, we can start solving things. Okay, so this is just math, and see what we get. By the way, you see how L canceled out completely and is no longer present in the equations?
Yeah.
Now, and that was a given, so that means it's actually not relevant. How about the mass? Do you feel the mass will be in the answer?
Yes. Wait.
So we're looking for this guy, right? Remember, the first instinct to do is to check units. Mu is unitless, right? So whatever combo we got out of the givens, it should be unitless. L is already shown not to be present. So we only have mass and theta. And mass is kilograms. There is no way to cancel kilograms if you try to stick the mass in the answer. Okay? That tells us that the mass is not going to be irrelevant. The answer for mu is only going to depend on theta. It's going to be some trig combination of theta. Okay? So that's pretty much it. Let me just write this as mu n1. So perhaps I'll start with these equations because they're simpler. So I start with the x equation and say that n2 equals mu n1, and then n1 I'll take from the y equation. So it's mu mg. Okay. All I need to find now is m2 because then that way I can solve for mu. And I look at equation A right here. Okay. From equation A, I get that n2 equals mg over 2 times cotangent theta. Okay. Now from these equations, mu equals cotangent theta over 2. Do you guys agree?
Yes.
Okay. But now we still have equation B, for example, or equation O. And we can check if they're consistent or not. Okay, so this is the issue, remember. So if you have more equations than there are unknowns, you got to be also super careful. So let's box this for now, and then consider what happens to equation O. So N1 is mg. F is the same as N2. So that is just 2N2, right? And that is equal mg cotangent theta, as we just found from here.
Aren't they negatives of each other? Or are we taking like, oh, is that absolute? Okay.
No, these are already magnitudes. Everything in the equations
are
magnitudes. Yeah, I skipped that step where we took care of directions. Folks, do you see what we're getting here? So cotangent times sine is cos. Oh, and 1 over 2. Right? I'm borrowing this expression from down here. So 2's cancel. And you see everything cancels out. So we get an identity. Equation O becomes an identity. Do you see that? Okay, that's a relief because who knows? We could have gotten an inconsistent equation. Okay, do you guys have any questions for me?
Wait, you divided by sine theta on both sides, or?
Do you mean here?
Yeah.
No, I just simplified. Cotangent times sine is cos.
Oh, okay.
Okay, at home, I'll assign you a problem to do the same thing if there is also friction with the top, with the wall. So assuming the same mu, what would be the mu? Okay.
Okay.
Okay, let's consider another problem, and I think I want to use one of my PowerPoint slides for that. Some pre-drawn figure. Oh, Andrew, I didn't ask you. Are you familiar with statics? Okay.
Yeah.
Okay. So you can tell me if something is missing. Okay. Let me copy this. Okay. So this is a shelf, and this is a string. So let me tell you what's given. Given the mass of the shelf, its length, L, L, let's say we're given this angle, theta, and the distance where the string is connected. We want to find the tension in the string necessary to hold the shelf. Oh, I assume that here you have a hinge, frictionless hinge. Is that clear? So if not for the string, the shelf would just drop down, like it will swing down. Okay. So does anybody want to do it? You don't have to know right away everything, just know how to start and just work it out. So I'll give you a couple of minutes to think about it, and then tell me if you want to explain this problem to the class. Okay, folks, what do you think?
What's it called? Torque is FL, where F is the mass, where F is the force of gravity, but
Well,
oh wait, yeah,
okay.
you have to use
Yeah. Well,
inertia.
let's do baby steps. So we start with like all the forces acting in this diagram, and then writing down the equations and everything. So what are the forces acting here?
Gravity.
So where is it applied?
At the tip of the bar. Well, actually everywhere,
Right.
but at the center of mass.
Right. Yes, but effectively, if we were to represent that with a single force, that would be at the center of mass.
Yeah.
Okay. What else?
Tension.
Tension. So now tension applies to two places. Right, it applies to the shelf, like so. And then it acts on the wall, but we probably don't want to really consider it. It's not helpful. So let's just talk about this one, tension. And this is what we need to find. Okay, what else? Anything else?
Torque of the bar.
Oh, yeah, well, we'll talk about torques later. We need to first finish with the forces. And then we'll talk about torques. Because torques are produced by forces, right? Normal force from the wall, I assume acting on the shop. So this is the tricky thing. So Vincent, I'm referring to the force in the hinge. In here.
I think yes.
Okay, yes. So this is a tricky force. So hinge forces are tricky because it's hard to tell their direction. It could be anything. Like normal force is always perpendicular, that's easy. But hinge forces can be anything. In fact, I want to put a second question here. I want us to find that hinge force. Okay, let's call it FH. And it's a vector, so we'll probably need to find both magnitude and direction. So for now, I guess, do you have any guess as to like which way it points? Out, you mean out as what? Left, right, tilted?
Right.
Straight to the right?
A bit upward.
Okay, let's draw it. If we find out that it's different, we'll fix that. But it's really hard to tell when you start the problem which direction the hinge force would point. It usually follows from your math later on. Okay, that should be it, right? So
Yeah.
three forces. Now let's start writing the equations down. Okay, guys, I'll just do the standard X and Y axis. And then what do we have? What do we have on the x-axis? Yeah, and let's label the angle of the hinge force as alpha, and that's unknown. So what should I write for the x-axis? Can somebody spell it out?
Fn cosine theta.
FH. Okay.
Oh, is that h? Sorry. And
cosine alpha, you mean?
alpha and
Yeah.
t cosine theta.
Yeah. Technically, I should put the minus here, right? Because it's
yeah, minus
to the left. Or we can just say equal t to cosine theta. Okay, good. How about y?
T sine theta equals mg. Plus, I'm sorry, wait. T sine theta plus fh sine theta.
Uh-huh.
Oh, no, I think that fh sine theta should be. Oh, well, it doesn't matter because like it'll depend on which way.
It will, yes, but let's just be consistent with our picture. That just helps a bit, okay? So fh sine theta, oh, sorry, sine alpha.
Yeah, if alpha is negative, then it'll just turn negative, so.
Right, exactly. So that's equal mg. So these are force equations. Now, how about torques? We need to pick some axes. What do you think would be good axes to consider?
The hinge.
Okay, let me call it A. Yeah, thanks, Vincent. Center of mass. Thank you, Vincent.
Yeah, center.
So let's call it O. Anything else? Maybe this point as well. You probably already have some intuition that not all of these equations will be independent anyway. But the rule of thumb is that a good axis is the one that has at least one force pass through it, because that will kill the torque of that force and make the math easier. So I would start with the axis A because that kills the unknown force, F hinge. So tension produces a counterclockwise torque, gravity produces clockwise torque. They compete, but we can set their magnitude, torque magnitudes equal. So what should I write? Who can spell it out?
Mg L.
L.
That's
what
like,
is the arm length of mg?
Oh, I was thinking of through A. Are we doing through B or through O?
Well, A is the axis of rotation, right?
Yeah.
The force is mg, and that has an arm length of L over 2.
Oh, okay.
Make sense?
Yeah.
So I put L over 2 here for the torque of gravity, and then tension. What do we do with the tension? So the arm length is d, so I put TD, and then we need to figure out the trig. So do I put sine or cosine theta? What do you feel? Andrew, what do you think? Is it sine theta or cosine theta?
I think it should be sine since it would decrease, right?
Yep, that you can easily do So you can easily use the trick to figure it out. Exactly. You see it? You see how, guys? If theta is 0, the torque of tension should be 0. And the trig function that does that is the sine function. Okay, that's good. In fact, this one equation allows us to find the tension right away. Okay, so let's do it and answer the first question. T equals mg L over 2d sine theta. So that's how much tension has to be in the string. Okay. The rest will be finding FH. So we need to write some equation that contains it. So what do you guys want? Let's do 0.0 maybe. So who wants to spell out? So gravity doesn't contribute, but these two guys can compete. Подождите, ну подождите. Okay, folks, I see something in the chat, but that's not about that. Okay, tell me what the issue is. Okay, Vincent, what do you think? Let's finish this problem and take a break. It's taking longer than it should have. Okay, Vince. So this is what the hinges torque. Okay. So, folks, do you agree with Vincent?
Yeah.
Okay. That seems right to me. FH L over 2 sine alpha. And that equals to the counterclockwise torque of tension. That is T L over 2 sine theta. Okay. You can cancel the L over 2 part. And from here, well, that's not enough yet, right? Let me see, there is something in the chat. Oh, yeah. My bad. Back up. Thank you, Vincent. Yeah, the arm length of T is not L over 2. It's actually a D minus L over 2. So thanks for catching that. Sine theta. Okay, but anyhow, you see there are still two unknowns here, alpha and F hinge. We need another equation. So we need this equation, for example. That will give us FHL sine theta or will it not? It probably won't help. It's not independent. Folks, do you see that? That equation B will not be independent, much like it was not independent in the previous problem. It will be combination of A and O. So let me back up. Just say not independent. Okay, so, but we of course can use one of the force equations. So folks, do you know how to finish this math, or you want me to tell you? Okay, who knows how to finish? Please put a thumb up. Okay, let me explain. So I think the easiest way to do it is to take equation O and divide by equation X. Then on the left-hand side, you have L over 2 tangent alpha. On the right-hand side, you have D minus L over 2 tangent theta. So from here, you find the alpha. Okay. It may not be like super easy, but say if you have some numerical givens in the problem, that should be straightforward. Okay, from here you find alpha. And once you found the alpha, then you can, of course, use one of those equations to find FH. For example, X equation would probably be the easiest. And substitute into X. Okay. Again, usually these problems, they come with specific numerical givens, so you can just do things numerically. Okay, so any questions, any questions about a problem like this? Abhijit, look like you wanted to say something.
So like Is the center of mass usually the thing that you use for axis? Like mass and then another hinge? Or does it depend?
Well, the rule of thumb is that what makes a good axis is an axis that has at least one force passing through it, because when you write the torque equations, or the torque equation for that particular axis, the force would not be contributing. Okay, the more forces pass through a specific axis, the better that axis is for your considerations.
I see.
Okay, in this particular problem, again, in the beginning, you have no idea what the hinge force does. So it helps to actually choose A as your axis, because on that axis, the hinge force won't contribute. Okay, that's what we did. That's what equation A did for us. It gave us the tension, but once you found the tension, you can use some other equations to figure out the hinge force. Okay, so then let's take a break, a 10-minute break, and then we'll switch to gravity. Okay, now it's on. Thanks, Andrew. Okay, so the topic is gravity. Yes, we did use gravity already, but now we'll do it the right way. Let's recall what we had before. The old formulas. Had force of gravity equal to mg, and also had gravitational potential energy that was given by mgy, where y was measured with respect to some pre-chosen zero level. Or sometimes it's also called ground level, especially in quantum mechanics. Ground level refers to the lowest possible energy state. Okay, so this is what we had before. Now let's understand what's wrong with these formulas. Like, they were obviously good enough for us to do stuff, but they're not ideal. So what's wrong with these formulas? When do they work? And then we'll understand when they don't work. Folks, are you with me?
Yes.
Okay. So when do these formulas work well?
For
When
big objects?
Okay, one person at a time. Andrew?
I think they work well for big objects with like big distances.
Okay. Abhijit?
Isn't it when y isn't too big and m isn't too big? I thought it was the opposite.
So the formulas work well when y isn't too big. So basically, in other words, near the Earth's surface.
Oh, my bad. I was thinking of the other FG. My bad.
Okay. So let's understand what that means numerically. So this is Earth. This is Earth's radius, and we'll use this symbol to represent that. As you may remember, the radius of the Earth is approximately 64,000 kilometers, or 6.4 million meters. Okay, so anything that's significantly smaller than this distance should be fine. Even if you look at like the Mount Everest, which is roughly 9 kilometers tall. That's still much less than this. Okay. So even for Mount Everest, this formula should work pretty well. For satellites, do you guys know the typical altitude for satellites?
Way above the stratosphere. I think it's like R over 2 or something.
Actually smaller than that. And listen, I just noticed your previous comment. Thank you for that. Satellites typically fly at like a few hundred kilometers. Yeah.
Oh, so R over like 100 or 50.
So something between maybe 200 and 600 kilometers. So this is still significantly less than the radius. You cannot really disregard the fact that force of gravity gets weaker with distance, but it's not super significantly weaker. Okay. So I just jumped ahead, I guess. I disclosed the secret that force of gravity gets weaker with distance. And as you probably know, the first person who actually quantified that was your old friend, Isaac Newton. And what we know by Newton's universal law of gravitation. So when does it become relevant? Of course, it becomes much more critical when you try to consider, say, moon orbiting the Earth or Earth orbiting the sun and things like that. Yeah, but we will study electrons and protons after we finish this. So let me maybe comment on one word here, the word universal. Does anybody know why it's called universal?
It works for any single body.
Well, at that moment, you should realize that people thought of, say, Apple falling on Newton's head as a totally separate event or phenomenon compared to, say, astronomy, astronomical motions. And it really was a genius idea that both of these phenomena are governed by the same law. Both Apple falling and, say, moon orbiting the Earth or planets orbiting the sun, they're governed by the same equations, by the same principles. That was a really non-trivial idea at the time. Okay. So what is it? Well, Newton figured that the gravitational force exists between massive objects. And he did say objects, however, it's more correct to say point particles. Okay. And we will, and then we'll discuss what happens if some objects are not point particles. So he figured the more massive the objects are, the stronger the force. So he put both masses of two objects in the numerator. Well, let me illustrate that. You have two objects, two point particles, M1 and M2 separated by distance r. Then they exert equal and opposite attractive forces on one another, directed along the line connecting them. So this is Fg, and this is like Fg prime, which is equal and opposite. Okay, so, but what we're writing down as Newton's law of gravitation is the magnitude of that force. So it's proportional to each mass. That means if you say double this mass, the force doubles. If you double this mass, but keep that constant, the force still doubles. If you double every mass, the force quadruples and so on. He also realized that the force weakens with distance, which made sense, but there are still a lot of options. It could be pretty much any function that decreases with distance. So again, he realized it's a polynomial, not just some polynomial, it's actually r squared. That's why we call it the inverse square law. Now, as a physicist, what do you immediately think when you look at this proportion? Because your ultimate goal is to turn this into an equation, right? You want to write something like this: force equals blah blah blah. So would this work if you just put the quality, the equal sign? Would this look okay? What do you think? Folks, are you with me?
Mm-hmm.
Oh, okay, yeah. Yeah, I need to bring the chat window up here. Yeah, but what's the motivation for that constant?
Well, it's just like something to correct for it.
Okay.
Because we know that it's correlated with the masses and the inverse square of the radius. But we need a coefficient to like correct it.
Correct what?
Well, even if there's a correlation, like 3 cans of soda to a package, like you need a coefficient.
Well, the main, I mean, this is partially true. So the main motivation, as Vincent put in the chat, is units. Because even if you like fix the numerics, more importantly, you need to make sure the units match. So if you look at it, what do we have on the left-hand side? We have newtons, right? Which is kilogram meter per second squared. If you look at the right-hand side, what do you have there? Mass times mass, that's a kilogram squared, over distance squared, which is meter squared. So this is like, these are different combos, right? These are not equal. So you need indeed to put that constant G to make this work. So now tell me what units should this G have? Okay, thank you, Vincent. Indeed, it's meter cubed over kilogram second squared. Yeah, it's a weird combo, but that's what it takes to make things work out. And numerically, you may also know G is 6.67 times 10 to the negative 11 meter cubed over kilogram second squared. So if you forget units, you can always figure them out from this equation. As far as the number in front, you can kind of sing it and it rhymes. 6.67 times 10 to negative 11, 711 kind of rhyme. Okay, so this thing, as you of course know, is called the gravitational constant or Newton's constant. It's one of the 3 fundamental constants of nature. So in electricity, the situation is a little bit more interesting. So we'll talk about it. possibly next year when we get there, because there things are not as straightforward. There are options. Okay, so now this works for point particles. Let me box this as well. So this works for 2-point particles. Now, what to do if you want to consider realistic objects, which are not point particles? So what about extended objects? So I'm going to outline the procedure for you. We're not really going to use it because you probably imagine what it takes in terms of math. So let's say you have one object of some random shape, and the second object is still a point particle. So this is M1, this is M2. So this is an extended object with some mass distribution. We already did it a couple of times, so you know the way to describe this mass distribution is to introduce the density function, rho of x, y, z. It tells you like locally how much mass is sitting in some elementary volume. And then what? You break break this object. You think of this object as a collection of point particles. So you like imagine breaking it in little pieces. Each piece has some mass dm that can be defined by the local density and local like little volume. And then for this particular dm, you have to draw the line and find the radius. All right. Let's say this is dm with the number sub I, and then this is r sub I. And then you write the force sub I that this piece exerts on M2. So F sub I equals G dm sub I times M2 over r sub I squared. But this is a magnitude. You really need to be careful and treat force as a vector. Okay, and that's attractive vector. Okay, df, because it's infinitesimal, small force. Okay, and then you have to switch, like you need to consider all these little particles, all these dm's, consider all the little vectors, add them up as vectors, and that'll give you the resultant force. So F12 total is the sum of Fi's vectors, which really boils down to an integral, which is three-dimensional integral, right? Over all the points, over all x, y, z's, so over the region occupied by one of rho of x, y, z. I'm putting a vector, and I'll define what that means here. Okay. And I shouldn't really be calling it f sub y anymore. I should be calling it f of x, y, z, meaning that for like a dmi has some coordinates, right? And they define the force. In reality, what happens is that you consider three separate integrals, for example, or one way to do it. You consider three separate integrals for the x, y, and z components of the force. So you need to compute three-dimensional integrals to get the force vector. Does that make sense, folks? It's not what you're really eager to do right away. Okay. Now, what if the second object is also an extended object, not a point particle? Then you kind of do the same for the second object. You consider it as a collection of DMs, and you label them somehow, and you introduce the density function, some other row, and you have to use different variables, let's say x prime, y prime, z prime, to parameterize the locations of those particles in the second object. And then you consider each possible pair, one particle from this object and other particle from this object. And then that gives you a single df, and then you add all those dfs. So what you really integrate over, you need to compute a 6-dimensional integral, okay, over 2 sets of variables, x, y, z, and x prime, y prime, z prime. And you need to do 3 copies of that because force is a vector and has 3 components. Okay, do you see the scale of the task? So you probably imagine that Newton was not really, did not really have too well developed techniques for doing that. But we do. We have computers that we can force to do it for us. So this is the outline how in general the force of gravity works for extended objects. So what also helps is the vector version of Newton's law of gravitation. So we can promote force into a vector by understanding that this radius vector can be made a vector. So if you say, let's go back a slide. So let's say M1 is your origin and you want to find the force acting on M2. Okay, then you can think of the radius vector that points from M1 to M2 and understand that the force that you're looking for is anti-parallel to that radius vector. Okay, so force of 1 on 2 is anti-parallel to the radius vector 1, 2. Okay, and how do you combine the magnitude and direction? So let me show you the standard trick, how it's done. So you need a unit vector that points in the proper direction. And you make a unit vector by taking a regular vector and dividing it by its magnitude. So you can say r hat is given by r12 divided by the magnitude of r12. And that magnitude is really what we called r. You can suppress the subscript. And then the force, a vector force, becomes Fg equal G M1, M2, that stays. But then what you have is this. You need to take 1 over r squared, as before, times this unit radius vector, with a minus, by the way. So the way it works is the following. R12 over r cubed. Cubed, not 3. Folks, are you with me?
Yeah.
Okay, yeah, so this is how you treat the vector force. Then you can plug it into the integrals and do some other stuff. Okay, now the good news here is that by some mathematical miracle, if one or more objects involved are spherically symmetric, then things simplify dramatically. Let's say if M1 is spherically symmetric, the end result of this integration is very simple. The force from 1 on 2 is still, or the magnitude of that force, is still exactly the same as if all of the mass of M1 was sitting at its center of mass. Okay, does that make sense, folks? So if M1 was a uniform, not uniform, if it was spherically symmetric object, doesn't have to be uniform. Think of Earth, for example, you know Earth is not, well, it's not even spherically symmetric because it's squeezed on the poles, but if we ignore that, still Earth is not uniform because it has a relatively dense core, less dense mantle, and then crust. Okay, so it's not uniform. However, it's spherically symmetric because you rotate it anyway and it still looks the same. So for those objects, the force reduces to just the regular Newton's force of gravity, assuming that the extended object collapsed to its center of mass. Okay, so it's just G m1 m2 over r squared, and the r is the distance from m1's center of mass. Okay, just to be clear. So this is the distance between m1's center of mass and m2. Okay, so with this in mind, let's consider some examples. So we know that on Earth, there is force of gravity acting, right? The old formula. Which is directed to the center of the Earth. So we know that on one hand, Fg was equal mg. But on the other hand, the new formula, so old, says that Fg should be equal gravitational constant times the mass of the Earth times the mass of the guy over what? Over distance squared. And remember what we just discussed in the previous slide. The formula works if you assume that all of the mass is sitting at the center. So the distance would be the radius. So put radius squared in here. Okay. So now our task is to compare and contrast. So if you compare these two formulas, and again, just a reminder, in physics, whenever you have a new, better theory, more wider theory, there is this correspondence principle that says wherever and whenever the old theory worked well, the new theory should be consistent with that. So that means near the surface of the Earth, this formula should give us the little g, right? So this should be the little g. And this is what we'll check real quick now, okay? Guys, please tell me, have you ever done it before? No? Abhijit, do you want to say something?
Like jump, wait, can you like done what?
Compute little g from the first principles.
Yeah, I think we did that in physics class once.
Okay, then we'll do it real quick. Okay, so and I'll do it without calculator. Okay, so let's just recall a couple of things. We know the gravitational constant as 6.67 times 10 to the negative 11 meter cubed per kilogram second squared. The mass is the mass of the Earth, which is approximately 6 times 10 to the 24th kilograms. And the radius, as I already mentioned, is approximately 6 million meters. Oh, sorry, 6.4 million meters. Okay, so let's compute this combo. So little g, I put a question mark for now, still to be shown, is gm over r squared. This is 6.67 times 10 to the negative 11 meter cubed over kilogram second squared times 6 times 10 to the 24th kilogram over 6.4 times 10 to the 6th meters squared. So, folks, it's a good habit to have. I'm trying to remember, we did it before, and I don't remember. So whenever you deal with things like this, do it in 3 steps. From the back, actually. First, collect all the units and see if they work out fine. Okay, so that is collecting meter, kilogram over kilogram second squared, and also you have meter squared on the bottom. And at this point, you pause and check if this combo is making sense. If we simplify it, what do we get? Kilograms cancel, meter squared cancels. We get meter per second squared. Is this the right combo for us? Yeah, Vincent, I don't think calculator would do units for you though. Folks, is this the right combo? Yes or no? Guys, are you with me?
Yeah.
Yeah, we're looking for acceleration, so this is the right combo. Okay. Yeah, if you can turn the cameras on, that would be helpful because I can't really tell whether you're following or not.
I completely forgot it was off.
Thanks. Okay, so now the second thing you collect is powers of 10. So you have 10, negative 11 from the gravitational constant, plus 24 from the mass, and then negative 12 from the denominator. Okay, and this is 10 to the first, right? And finally, you collect the rest, which is not that bad anymore, 6.67 times 6 over 6.4 squared. Okay? And I'm going to argue that, so this is 6.4 times 6.4, this is slightly greater, this is slightly less. I'm going to argue that this is approximately 1. I made some roundings as well. So because 6 is not really 6, it's 5.89 or something, and this is not really 6.4, it's 6.371. So I did some roundings already. So this is good enough. And if you put it all together, then you get roughly 10 meters per second squared. And this is exactly what we thought of G before. So now you know where it comes from. It comes from some constants. The fundamental constant G plus the Earth parameters, and the relevant parameters are the mass and the radius. So if you do this for the moon, for example, you'll find that the acceleration of gravity on the moon is approximately what? How does that compare to Earth? Who knows?
1/6?
Yep, for almost 1/6, almost precisely 1/6. Okay, that is if you repeat the same analysis. You put moon's mass, radius squared, you get roughly 1.7 meters per second squared, which is roughly 1/6 of Earth's G. Okay, any questions so far? No? Okay, so let me use this knowledge to tell you something interesting. So the next thing to consider is cosmic speed. Who knows what they are and can explain to others? If nobody knows, that's fine. I'll just explain, but I'm curious if anybody already knows. No? Okay. So there will be three. First, second, and third. And they have to do with projectiles. Okay. So let's consider the following. So let's say you have a table. And you launch a ball horizontally. You know the ball will follow some parabolic trajectory and fall down. Now, suppose you double the speed. It will go slightly further. Well, not slightly, but twice as far. Okay? What happens if you keep increasing the velocity? What can you no longer ignore? Okay, let's say we still ignore air resistance. What if the speed is very, very large? What becomes important? So the speed is very large. The distance traveled is very large. At large distances, what can we no longer ignore?
The circularness of the Earth.
Exactly. So we should really incorporate that Earth is curved, right? It's spherical. Obviously, it's not up to scale. But what may happen at a certain speed is that as the projectile is falling, it is approaching the center of, well, it wants to approach the center of the Earth. But the surface of the Earth is receding just because of the curvature. And what may happen is that the distance between the projectile and the surface doesn't decrease. What will we have then? We'll have the projectile orbit the Earth, constantly free falling, but never actually hitting the ground. Does that make sense, folks? Have you thought about it before? Yeah. Okay. So what remains for us to do in the next few minutes is actually to quantify that. See exactly how fast the projectile needs to be launched so that this happens. Okay. And the minimum speed that makes the projectile orbit the Earth is called the first cosmic speed. Okay. So if you want first cosmic speed is the minimum projectile speed to orbit or to never fall, to never hit ground. Because it's always falling, it's just never hitting the ground. Okay, and I emphasize the word projectile here. It's not a rocket that has source of energy and engine and so on. No, it's just a projectile that you kick once, and that's it. Okay, I'm going to take a kind of, hands-on baby approach, and then we'll make it more rigorous next time. So first, I want to recall one interesting thing that near the surface of the Earth, when acceleration of gravity is little g, and you drop an object, it will go down by 5 meters in 1 second. So in 1 second, it will fall precisely by 5 meters. Does that ring a bell? Okay, so if you think of like delta y equal 1/2 gt squared, assume that g is 10, then in 1 second it gives you 5 meters. Okay, so 5 meters in 1 second. Okay, and I'm going to actually call it h. So say projectile has fallen by height h. Now what I want to do, I want to find how far it needs to have traveled so that the curved surface has receded by h. Okay, I'm going to call that distance x. Okay, and once I found the x, I would know this is like how many kilometers per second the projectile needs to be traveling. That gives me the speed, right? X per second is the speed. Okay, so now this is a purely geometric question, really. If you look at the Earth, let's say this is your launch point, right here on top. And then let me do another. So these are both R of Earth. And then this distance is indeed x, and this is h. Okay? Are you guys okay with this geometric construction? So you travel by x to the right, and that makes the h of height above the surface. Okay? So how do we figure out the x? Well, it's easy to write down the Pythagorean theorem here, right? R squared plus x squared equals r plus h squared, right? And then expand the right-hand side, have it as r squared plus 2rh plus h squared. So you probably noticed that the leading terms, the r squared, cancel. But if you look at the remaining two terms here, you should see that h is a few meters. Here you have h squared, and here you have h times the radius of the Earth, which is a few million meters. So this last term is really negligible compared to the other one. Okay, so that gives you x equal, or approximately equal, to RH square rooted, right? Because this is x squared. Okay, and if you do the math, that's actually very quick to do. Have 2 times 6.4 times 10 to the 6 times 5. Now 2 times 5 is 10, 10 times this is 64. Very easy to take the square root. So this is 8 times root of million, which is 1,000. So we get 8 kilometers, 8,000 meters or 8 kilometers, or if you're more comfortable with miles, this is approximately 5 miles. So the first cosmic speed is equal 8 kilometers per second, or 5 miles per second. So just to give you a sense, how long is the central part? Who knows? I'm just asking in case you may know instantly. If not, then never mind. So just to give you a sense, this is a pretty fast speed. Okay. The projectile will orbit the Earth if it makes 5 miles every second. Okay. So that means you like from your home to school takes a few seconds. Okay. So if you go that fast, you'll never fall. Okay, any questions?
No, it makes sense.
Okay, so we're out of time. So next time we'll continue with cosmic speeds. We'll talk about the second and third ones and solve some other problems. So I'll see you on Monday. Oh, and watch out for the homework that I'll post probably tomorrow.
Oh, I had one quick announcement. We launched a fundraiser for the team, so if you guys can like contribute something, that would be great. I posted it on our server, so just keep that in mind.
Okay.
All right. Have a good day. See you guys.
Yeah. Bye.